Okay, limber up for this one because this is going to be a slightly longer than normal video just because the combined spectroscopic techniques method just is quite long. So do feel free to take a break during this video. After 5 or 10 minutes, just stop, take a minute to get your head together, have a think about what I've said. So here's our typical question. So we've got our graphs down the side here, and the question would be deduce the molecule. So figure out what molecule caused those graphs, and then the question will say justify your answer or explain your answer. And that's what this question is all about. If you just wrote down the identity of the molecule, you'd get a couple of marks. Most of the marks are for showing how you got there. So this is all about putting down all of your working, okay? And I should say, in an actual question, it's unlikely you'd have to analyse all 4 graphs. Probably they'll give you 2 or 3, and then they'll just tell you the rest of the information. However, as I don't know which 2 or 3 they're going to give you, we'll go through how to analyse all of them, and then no matter what they give you, you'll know what to do. So there is an order to analyse these graphs that will make it easier for you, and the order is to start with mass spec. So here's my mass spec graph here. From that, you should be able to figure out what the MR is and what the molecular formula is. And you'll notice I've given you the empirical formula here. This is our empirical formula. So stop the tape, see if you can figure out from the mass spec graph these 2 things here. When you're ready, press play, and I'll go through the answer. Welcome back. So what we can do is use our heaviest peak, our peak furthest to the right, our molecular ion peak, which is 46, and that will tell you the MR. So M plus is 46, therefore MR is. Notice I didn't just straight away say MR is 46. I showed my working. Yes, that's what this is all about. Not saying what you know, but also saying how you know it. Once I've got my molecular formula MR, I can compare that to the empirical formula MR. So my molecular is 46. My empirical, if we add that up, comes to 46. And that will tell you how many more times bigger your molecular formula is than your empirical. So this is telling me my molecular formula is 1 times as big as my empirical, therefore my molecular formula is my empirical. So that's just going to be C2H6O. If this final number hadn't come out as 2, then my molecular would be C4H12O2. If this had come out as 3, it'd be C6H18O3. Right. So that's all we can get from mass spec for now. So let's move on to our second graph, which is the IR spec. Now from the IR spec and your data sheet, your handy data sheet, you should be able to figure out what bonds are in there and therefore what functional group. So have a crack at that. Welcome back. So by looking at our IR graph here, we can see there's a peak at round about just above 3000. So that's going to be an OH peak. Problem is though, if I can show you this data sheet, there's 2 OH peaks. There's one for alcohols and phenols and one for carboxylic acids. So we need to figure out which one it's going to be. Now what we can't do is look at the wave number, because they're too similar. If you look at the wave numbers, they overlap. What we also can't do is look if the peak is broad, because all OH peaks are broad. It's just carboxylic acids are very broad. So how are we going to tell which of the OHs this peak is? Well, we're really weirdly going to look for a peak at about 1,700. So if it was an alcohol, I would have a CO and an OH. If this OH was a carboxylic acid, I'd have a CO, an OH, and a COO. And COOs crop up about 1,700. I do not have a peak at 1,700, so I cannot have a COO, so it cannot be a carboxylic acid. So that's how you tell which of the OHs your OH peak is. So I now know this is an alcohol OH, and I'm going to write the bond down with the wave number in brackets afterwards. You might have also said there's a C single over there. That's fine if you did. You wouldn't lose a mark if you didn't say that because it's in the fingerprint region. But if you did, that's fine. And so all in all, we can conclude, therefore, we have an alcohol. And notice I used like the English word alcohol. I didn't say COH. I literally wrote the word. And that's what we can get from our IR spec. Next, we're going to move on to our carbon NMR. So that's this third graph here. And for that, we're just going to do a little table. We're going to do chemical shift and the environment that caused that shift. So my chemical shifts are, what's that like, 76 and 18? Something like that. Give or take. So again, stop the video, place Snapseed on your data sheet. It really helps if you look back at previous information, especially the functional group. So always be looking back. That's why we're doing it in this order. Welcome back. So 76 is going to be the C to O environment, and 18 is going to be the C to C environment. If we thought we had a benzene ring, it would in particular be useful to write down the total number of carbon environments. So it might be a nice habit just to get into 2 carbon environments in total. And when we do benzene rings, you'll see that really, really helps. Okay, so on to the big boy. I would maybe stop for like a minute or two just to give yourself a rest before we get into this, because this is there's a bit to it. So for the hydrogen NMR, we have a 6-column table. Ooh la la. And they come in pairs. So the chemical shift will tell us the environment. The splitting will tell us the number of adjacent hydrogens, the n+1 rule. And then from the relative peak area, that can tell us the conclusion. Now again, I'm abbreviating here because I don't have much space on my board. Don't abbreviate in the exam, right? Write the whole words out. Okay. Now, 3 of these columns we can fill out just from the graph. So my chemical shifts we can fill out. I would start from the left and work your way to the right, because if you look at your data sheet for hydrogen NMR, there's loads of stuff on the right, so it's hard to pick, whereas on the left, it's usually quite obvious. So let's start with the easiest stuff to make it easier for ourselves. So starting from our left and working across, I got chemical shifts of about 3.5, 2.4 and 1.2, something like that. My splitting is a quartet, a singlet and a triplet. So I'm going to write down again like the English words. And my relative peak areas are 2, 1, 3. So from the graph we can fill out these 3 columns. And then from the chemical shift we can tell the environment. Again, always look back at your previous information, especially the functional group. So stop the tape, try and figure out what 3 environments these 3 things must be. Start when you're ready. Okay, welcome back. So again, I know it's an alcohol, so at 3.5, from my choices here, like, yeah, okay, technically it could be a H to C to Br, but alcohols don't have bromines in them. If we look at our molecular formula, there's no bromines. So by using our previous information, we can see that must be a H to C to O. So I can write down H to C to O. Now we know it's an alcohol, so we know it must have an OH, and OHs are always singlets. They don't cause splitting, and they don't get split. So I know that the singlet must be my OH. And then the triplet at 1.2, that's going to be a H to C to C, or H to C to R, whatever you prefer. That's our first column done. Next we can move on to splitting and use the n+1 rule in reverse to figure out how many adjacent hydrogens must have given that splitting. So basically a quartet is 4. What number do you add 1 to make 4? 3. So next to this quartet must have been 3 adjacent hydrogens. Have a crack at it for the rest. And again, pause, press play when you're ready. Welcome back. Well, the splitting for OHs is always a singlet. So you can't really tell anything about that because they're always a singlet no matter what. And a triplet would have 2 adjacent hydrogens because 2 add 1 is 3. Okay, now come the 2 fancy tricks. This is what makes this table really work. First of all, we're going to fill in our conclusion column. Now, that is a combination of the environment column and the relative peak area column. The environment is a H to C to O. My relative peak area tells me I have 2 hydrogens in that environment. So that must be a H2C to O. I have an OH. I have 1 hydrogen in that environment, so that's just an OH. And then I have a H to C to C, but I have 3 hydrogens in that environment, so I must have a H3C to C. So that's the first fancy trick, combining the environment and the relative peak area to get your conclusions. These are like jigsaw pieces. These are chunks of your actual molecule. So this is by far the most useful column. All we need to do now is stick those jigsaw pieces together in the correct order to get our molecule. Just to make a little bit more space in my board here. We don't need this anymore. So if we want to stick the jigsaw pieces together in the correct order, wouldn't it be handy if we knew which jigsaw pieces was next to each other? That'd be really handy because then we can know to slot them next to each other. Well, there is a way of figuring that out, and that's by doing something called cross-linking. So here's the red pen, and here's a black pen. This is going to sound obvious, but if the black pen is next to the red pen, and the red pen is next to the black pen, then the pens are next to each other. Hopefully we got that. Let's have a look here. Let's call these environments A, B, and C. Just so you know which ones I'm talking about. If we look at environment A is made up out of 2 hydrogens, and it is next to something that has 3 hydrogens. Environment C has 3 hydrogens, and is next to something that has 2 hydrogens. We have a cross-link between environment A and C. Has 2 is next to 2. Has 3 is next to 3. Well, then they must be next to each other. So this chunk is next to that chunk. So some teachers ask you to write that down in the conclusion column. That's totally fine. Some people ask you to write it afterwards as a separate thing. Whatever your teacher asks you to do, we're going to combine these 2 chunks together because they're cross-linked. That tells me this carbon is next to that carbon. So I'm just going to write that out. I've got an O with a CH2, and next to this carbon must be that carbon because of this cross-link. So this carbon here is actually that carbon there. They're the same carbon. So there's a little bit of overlap between your jigsaw pieces. And so I can add on my CH3. Now, what some teachers prefer you to do is write the CH2 over there and just underline the one that is caused by this peak. Whatever your teacher asks you to do is fine. I prefer to just kind of do it afterwards separate. And then finally, all we need to do is add on peak B, our chunk B, which is the OH. So we've got the molecule. So 2 tricks to really remember. To get the conclusion, we combine the environment and the relative peak area, and that gives you your jigsaw pieces. To know which jigsaw pieces are next to each other, to cross-link, just see if your number of adjacent hydrogens and RPA link up, if they're complementary. And then very, very finally, last thing I promise, we need to go back and check our mass spec one last time and just check to see if we can get the fragments we want. And again, it's just a little table, mass spec and fragment. I've got 2 fragment ions, 15 and 17. Stop the video. The rule is, for OCR, you can only break 1 bond to get your chunk, but you can break different bonds for different chunks. So have a crack at that. Welcome back. So we're going to break this bond here to get a CH3 at 15, and then separately we're going to break that bond there to get an OH at 17. And then don't forget, these are fragment ions, so they must have a positive charge. And that is the full combined techniques method. There's bits of that, especially this table, where you're still feeling a bit like, oh, I definitely haven't 100% got that. That's fine for now, right? Maybe go back and watch that part of the video again, try a couple of practice questions. This often does take a little while to click, so just keep working at it. It's not the easiest thing, but pretty much all students, it will click at the end. You just need to keep working at it.